Okay, good morning, everybody. So let's get started. Um, First of all, I uploaded the class lecture video for the last class. Uh, have you noticed that?
Yes.
Okay, great. So therefore, after each class, always like I will be uploading the video in that way. So first of all, there are class lecture notes in on folder, and then you have noticed class lecture videos. So there I will be uploading the videos always. So like you have double chance. Before coming to class, you will be looking those class lectures, material or notes, and then after the class. I mean, in addition to that class lecture material, class lecture video. So then it will help you a lot. And then yesterday evening, I sent you an email. Although day before yesterday, I uploaded the updated class lecture too, but then later I found out that there was an issue in the audio voice. And then later I fixed that and again I re-uploaded yesterday evening. Did you receive my email, everybody?
Yes.
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 Okay,
Yeah, I got
okay.
it. Yes.
Okay, thank you. And then I think you have noticed that I have added my voice at each slide. Yeah. So this means that you have to scroll on slide on at a time, and then at the bottom part there is a audio sign or symbol. If you take your mouse and click there, then it will play, and you can see my voice. So therefore, the goal is that by looking the material, if you can't understand or what's that slide about, if you just listen to my voice, then you will get an idea of what I am explaining in that slide. So in that way, I mean, I will be adding my audio voice to each and every class. So before coming to class, you all will be looking that on, and then during the class, I will make the recording, and after the class, that will be uploaded, that video. So therefore, kind of two things. One is without video, other is with the video. So double chance. Okay, so now let me share my screen. Can you see my screen?
Yes.
Yes.
Okay. So the RLC circuit. So have you looked at these slides? Did you get any chance or you didn't look at?
I went over it. Yeah.
Okay, so do, do you understand something or like I should go over from the beginning?
Yeah. When I read it with an addition to the book, it helped a lot. So
Okay, thank you. Okay, so let me quickly go over and then whatever questions and comments you have, you could ask. And also I will be explaining through whiteboard. Uh, this is chapter 9 from the book that we are following. So the title goes RLC circuit, resistance, inductance, and capacitance based circuit. So uh, in the DC circuit course, you all have studied about RL and RC circuit, basically the transient. And then when the circuit has only RL or only R and C, that represents first order circuit because that involves the first order differential equation. But once in the circuit, there is presence of all three components R, L, and C that will represent second order circuit because it involves second order differential equation for any voltage or current that you want to calculate or find out. Now, I have written here, you see that second order circuit consists of resistors and the equivalent of two energy storage elements. Now, see that, like I am going to the next slide. So everybody see this figure. So the top two figures, the series circuit and parallel circuit, definitely both circuit involves all three components R, L, and C. So A and B, definitely those are the second order circuit because they will give you the second order differential equation. Now everybody say circuit number C, there is a voltage source and then there is R1, R2 and L1, L2. You see, in this circuit, there is no capacitor. But this does not mean that this is the first order equation, first order circuit. This is the second order circuit. You will be looking the component L and C, whether you can make equivalent or not. So can you make equivalent of L1 and L2? No, because in between there is R2. So therefore this is parallel, but then this is series, and then this is in series with R2. So there is no direct connection between L1 and L2. So you can't make the equivalent. So that's why, like this is on loop, this is other loop. So this is the second order circuit. Now everybody say, for example, there was no R2. Only R1 was present, but R2 was absent. So this means L1 would be parallel L2. In that case, you can make equivalent. So if you make equivalent, then it would be like combination of R and on equivalent. That would be the first order circuit. But here the issue is there is R2 between L1 and L2. So this is the second order circuit. Similarly, look the figure D. This is current source based. There are two capacitors, C1, C2, but between them there is R. So again, you can't make the equivalent. So this is also the second order circuit. So therefore, all four like A, B, C, D are the second order circuit. So therefore, again, I am going back to first slide. So see the definition of second order circuit. It consists of resistor and the equivalent of two energy storage elements. Now, today we will be discussing about the characteristics of second order circuit, in particular the source-free parallel RLC circuit. And then later we will be looking source-free series RLC circuit and then followed by some numerical examples. Now, why we are looking the source-free parallel and source-free series circuit? Because they provide natural or transient response. So probably in case of DC circuit, I mean circuit analysis on course, you all have studied the RL or RC transient circuit. And you notice that there were two responses. For example, you have a RL circuit and that is powered by a DC source, by battery. Then it will provide steady state response, or it is called forced response. If you suddenly take out the DC source, but still there is an inductor and capacitor, they will store energy. So that's why they will provide some natural response, which is called the transient response. So therefore, everybody you will keep in mind, when it is source-free circuit, the assumption is that initially there was a source with the RLC circuit. Suddenly the source is disconnected. At that time, because there is L and C component, and they will store energy. So you all know the property of inductor and capacitor. If it is powered by DC, then they can store energy. So because they can store energy, even though there is no source, it is source free, but still for some time, it will provide some response. That response is called natural or transient response. And when there is source included, that time it is called steady state response or the forced response. So therefore, let's have a look the characteristics of source-free parallel RLC circuit. So let's jump to slide number 3. So everybody see, so left side, this is that source-free parallel RLC circuit, R, L, and C. and I have marked the polarity, you see, plus, minus, plus, minus, plus, minus. I'm assuming that on the top node, the voltage is V, and then the bottom is reference, meaning that this side is like grounding. Now, everybody see this is a parallel circuit, but there is no source. So here, the assumption is that initially there was a source connected. For example, there was a current source, or there could be a voltage source, and the system was running, circuit was running. Suddenly, the source has been disconnected. But because, as I told you, because there was L and there was C, so inductor will store the energy by using half L I square. You all know. And in case of capacitor, half C V squared. So because inductor and capacitor will store energy, therefore, if you suddenly disconnect the source, this means if you make it source free, but still it will have voltage and current for some time, not for indefinite period, for some time. That is our point of interest. That is our goal today. We want to find out what is the voltage and current look like, provided that there was no source connected. Now, it depends on the initial condition. So therefore, to solve this type of circuit when there is no source, it is source free, first you have to know what are the initial conditions. These two are the initial conditions. So everybody see, once suddenly the source has been disconnected, but by then, because capacitor stored energy, so it gained some voltage. So that's why everybody, the assumption is that V at t equal to 0 time. So this 0 means at t equal to 0 time, the moment when the source has been disconnected. So that voltage we are assuming capital V naught. Similarly, in case of inductor, current was flowing and inductor stored energy, so it will have some current stored. So therefore I t naught, this means at 0 time, equal to capital I naught, and you all know this relationship of the current and voltage across an inductor, 1 over L integration of minus infinity to 0 Vt dt. So therefore these two are the initial conditions. Now move forward based on these two initial conditions. Let's have a look. How does the circuit behave? That is our goal. So go to the next slide. Now this is that circuit that I showed in the previous slide. So everybody see at the top node, the common voltage is V. And this is the bottom node, this is the reference. So like this is the current flow direction, current flow, current flow. So we are applying KCL, Kirchhoff's current law, that you all know at top node. So therefore, what is the current across this branch? The voltage is V and resistance is R. So V over R. What's the current across the inductor? 1 over L integration of T naught to T. We are going at a certain time, for example, at time T, Vt dt, and then for capacitor, C dV by dt, and that equal to 0. So just I gave the equation number J. Now, second line, third line, just I am reorganizing. So everybody see what I am doing. I am making time derivative. I am making time derivative. You see the in the first equation, the problem is that this is, I mean, the differential term, derivative term, dv by dt, but then this is the integral term. So it is difficult to solve if if an equation has both integral and derivative term. That's why in the second line, what we are doing, we are making time derivative. So look, this is 1 over r and then dv by dt. The third expression, c d square v by dt square. But then the middle expression, you see, because this is integration. So if you make the derivative of this one, then it will give you the simply v. So this is 1 over L, this 1 over L and v. So we just made simply the time derivative of the first equation. And then here I am just rearranging the terms. First I am writing the second order term, c d square v by at first, and then this one dv by dt, and then at last this one, that equal to 0. So therefore everybody see, this is clearly a second order differential equation form. So this means this circuit is a second order circuit. Everybody, could you follow me so far?
I just had a question about the. So you're doing KCL at the V. Why we're assuming that all the currents are going into that node, none of them are leaving that node.
Yeah, leaving the node. Right.
Okay, so they're all leaving the node then.
Yes, exactly.
Okay, thank you.
Yeah. And then if you understand the second term, right? So we just made time derivative. Everybody understand the second line?
Yes.
Yes.
Yeah.
Okay. And then the third line, like equation number, just the rearranging. First I wrote d square v by dt square, then I wrote dv by dt just to make a good form or the good sum. Okay. Now we have to solve. You know what is our goal? Our goal today is to find out what is the voltage. How does the voltage look like? This voltage for this type of second order circuit, provided that there is no source connected. This means that initially there was source connected, but we have assumed that source has been disconnected. Then what? That we are looking. So now everybody see, this is our equation number A, and then we are assuming the solution V is A multiplied by e to the power st. So I think from the math class, you know that how does the solution of this type of differential equation look like. So based on that, we assume that, okay, this is the probable solution. Now, everybody substitute this value into equation A. Now, look here, first term, because we are substituting V, but there is d square V by dt square. So this means you have to make the double derivative, first derivative and second derivative. So therefore, look the first term, this C is this C, this is A, but then dv by dt is s e to the power st, and then second time s square e to the power st. That's why ca s square e to the power st. Then look the middle term. This is 1 over r. This is this, but then because dv by dt, you have to make time derivative. So s e to the power st. And then this is 1 over L and a e to the power st. And then from here, everybody see there is one common factor, which is a multiplied by e to the power st. So that is the common factor. So here cs squared plus s over r, and then from here 1 over L, that equal to 0. Now here you see this multiplied by this term, that is 0. But you cannot say this is 0 because that is our solution. We have assumed that is the solution. So this means that we have to assume that this part is 0. But you see this part, it is like s squared, there is s, and this is constant. So therefore, this represents a quadratic equation, which is called auxiliary equation or characteristics equation for this circuit. Everybody so far fine?
Yeah.
Yes.
Yes. So you remember in math, you have learned this type of equation like ax square plus bx plus c equal to 0. Exactly the same form. Like c s square plus 1 over r into s plus this constant, like ax square plus bx plus c equal to 0, that you have learned in math for quadratic equation. So now you see or what is our goal? What we are trying to achieve? Our goal is to solve this equation, especially solve for V. That we want to get. And that I have assumed V equal to that I am trying to achieve. Now, because this is quadratic equation, now we have to find out the roots. What are the solution of this equation? So therefore, in the next slide, I am just solving this one. So therefore, solve this one. Okay, so this is the expression S1 and S2. So can you guess how you would get that one? Everybody, do you understand how we can get this one?
Quadratic formula.
Yes, exactly. So therefore, let me just a moment. Let me share. Then I'm coming back again for everybody. You see what I am telling? X square plus bx plus c. This is the quadratic equation, and what is the solution of x? X equal to minus b plus minus root over b square. Sorry. For AC over 2a. Everybody, can you remember this one?
And was in high school.
Yeah, so this is the differential equation, ax square plus bx plus c0. Then this will be the solution x minus b plus minus root over b squared. This is b minus 4a and c. This is a, this is a. And then in the denominator, 2a. So therefore, you have to apply this on for that equation that I was discussing. Everybody fine with this one?
Yes.
Okay, yeah. Just you all have learned this one even in the high school, so you just remembered. So that's why you see there is plus minus sign here. So on expression will be like minus b plus this one. The second on x2 will be minus b minus root over this one. So exactly I am writing this one. So now I stop sharing and then share again. I was here. Okay, now everybody come back. So therefore, look once again. This was my last expression. Cs square plus s over r plus. So you just compare with that ax square plus bx plus c. Then you will be getting these two expression. One is you see minus, here is plus, and then here is minus. Exactly, and then I just reorganize the term. Okay, so we have two solutions, S1 and S2. After that, what we are doing, you see the first line, 1 over 2RC, I am replacing by symbol alpha. So where alpha is 1 over 2RC, that is the definition. And then inside the root, 1 over 2RC is alpha square, but then 1 over LC, I have written omega naught squared. This means omega naught is 1 over root over LC. So the same thing for the expression S2. Now here everybody see omega naught 1 over root over LC. This is called resonant frequency. This is very important, this resonant frequency. In filter chapters, we will be extensively discussing the significance of this omega naught resonant frequency. Also sometimes it is called undamped natural frequency. And the unit is radian per second. Radian per second. And then this term alpha 1 over 2RC, it is called Nepert frequency or exponential damping coefficient or sometimes simply called damping factor. And it is called Napier frequency according to French mathematician John Napier, who first invented this expression, this terminology. Accordingly, it is called Napier frequency. Okay, so therefore, everybody, you will be remembering these two terms. It will help you to solve the problem. I mean, later we are coming. Now, moving forward, we got solution S1 and S2, but then you see, our solution was V equal to A to the power A multiplied by E to the power S2. So substitute the value of S1 and S2 in this expression. So therefore, here everybody see, we got one solution V1 A1 e to the power S1 t with respect to S1. We have another value which is S2 A2 e to the power S2 t. So therefore, because I got two expression V1 and V2, just add them up. So the total solution Vt A1 this plus this one. Now everybody see that in the expression, in the solution, there are two constants, A1 and A2. And there are two other parameters, which is S1 and S2. Now everybody see, because this is S1 and S2, now look these expression. Here there is plus sign and here there is minus sign. Now if alpha is greater than omega naught, everybody see, if alpha is greater than omega naught, only then you will be getting plus sign here, right? But if alpha is less than omega naught, for example, this is 10 and this is 12, then you will be getting minus. So after making root, you will get the complex number. So therefore, the solution of Vt is dependent on S1 and S2, and whether alpha is greater than omega naught or alpha equal to omega naught. Everybody see, if this term is equal to this term, then this cancelled. So this becomes 0. So therefore, S1 is just minus alpha. So S2 is minus alpha. But if alpha is less than omega naught, then the problem occurs. It is the complex number. So that's why, according to what is the value of S1 and S2, there can be three conditions. So everybody say this one. There can be three conditions. What is the three condition? As I told you, if alpha greater than omega naught, this means S1, S2 are positive value. If alpha equal to omega naught, this means S1 and S2 will have that just minus alpha that I showed you, just minus alpha. Or if alpha less than omega naught. So now depending on three conditions, because there can be three values of S1 and S2, accordingly, the voltage response could be overdamped, could be critically damped, could be underdamped. So if you find, I mean, when we will be solving the numerical problem, that time this conclusion will help you a lot. And everybody, you have to remember this pattern. I mean, initially you don't need to memorize, just look the notes and you make practice. Over the time, like you will be able to memorize it. So what you have to do, I mean, what we are trying to do, we are trying to find out Vt for that parallel source free circuit. And what is its characteristic? How does it behave? That we are trying to find out. But then complexity arises because of S1 and S2. That's why, depending on three conditions, it could be overdamped, it is called critically damped, it is called underdamped. So I am coming that thing in next slide. And depending on three conditions, for example, this is the condition alpha greater than omega naught, then this will be the solution. Solution is as it is. Everybody see V2 equal to this one. So this is your solution. This is the characteristics. Now to solve the numerical problem, you have to find out those two constants, A1 and A2. Also, you have to find out S1 and S2. Once you find out S1, S2 and A1, A2, just substitute in this equation, then you are done. Similarly, if you find for any problem that alpha equal to omega naught, then this will be the expression Vt, you see, A1 plus A2 multiplied by 3, then whole thing in parenthesis multiplied by e to the power minus alpha t. On the other hand, if you find this one, alpha less than omega naught, it is called underdamped response. Then this will be the expression beyond cosine of omega d t. This is not omega naught. Omega naught is one thing. This is omega t. And here is the definition of omega t. Omega d is called damped natural frequency. Omega naught is called undamped natural frequency or resonant frequency. Omega d is called damped natural frequency and unit is radian per second. But everybody see, in this expression cosine and sine term is involved. This means this will look like the sinusoidal response if it is underdamped case. So therefore, I am coming back this slide again. So therefore, let's look. Yes, here is that expression. You see, this response is called overdamped response. You see, like it was going in that way. But if you see the envelope, it looks like it was coming and it did not go to like zero line. It is going, damping. Over the time, it will like go away. And then in this case B, which is called critically damped response, you see like it was going in that way and then soon it will meet zero. And then if you see that envelope, like it looks like it was about to go negative side. So somehow it did not go. It got critically saved. It was very critical condition. That's why it is called the critically damped response. But see the underdamped or the undamped, it is like oscillating because sinusoidal. So therefore, if you see envelope, it is like that, it is like that, it is oscillating and it will oscillate for a certain time. And this is like the dangerous for the system if there is oscillation. This is not desired thing. So therefore, I mean, depending on three situations, like you have to pick up either this equation or this equation or this equation. So far everybody understand like what we are trying to do. Like then once again, everybody say, this was our circuit and it was a source-free parallel RC circuit. My goal is to find out what should be the value of the voltage expression and what is its nature. That we are trying to say. So therefore, what conclusion I made? I made the conclusion that depending on the value of S1 and S2, there can be three conditions, three situations. Either alpha can greater than omega naught, or alpha could be equal to omega naught, or alpha could be less than omega naught. Accordingly, it can be overdamped, critically damped, underdamped. Accordingly, you have to choose the equation. And then, so therefore, in each equation, you see A1 and A2. A1 and A2 in the third expression, B1 and B2. Therefore, in each case, you have to find out two constants. And then S1 value and S2 value. And then this is the alpha value. This is the alpha value. But you can easily get those values. You see, this is the S1 expression. This is the S2 expression. And you know how to calculate alpha. This is the alpha value. This is omega naught value. So from the circuit parameters, you can find out these two. So then you can compare which equation to choose. Therefore, now everybody, let's have a look at an example, then it will be clear to you. Everybody will be fine. Okay, now everybody please concentrate very minutely. If you understand this problem and then the next problem, and then if you attend next class, then you are able to solve all the homework problem that I am going to assign you soon. So everybody please be concentrated. In figure 1, you see, this is the figure 1. Let R value 2 ohm, L value 0.4 Henry, C value 25 millifarad. Initial conditions are given. V naught at time t0 is 0 and I at time t equal to 0, 10 milliampere. So based on these two conditions, find out Vt for t greater than 0. So therefore, for this circuit, we have to find out Vt. That's the question. So I have written down the answer for you. Now, so what we learned for this type of circuit, parallel circuit, what is my solution? Either of these my solution. Therefore, solution could be either this one or this one or this one. Now, which equation to pick up? Now you have to come back. So what you have to do? Now everybody see my solution. What I have done? First I have calculated alpha. What is alpha? 1 over 2 RC. So based on the parameters, I got value 10. I got omega naught, that also 10. So this means what you are getting? Alpha equal to omega naught. Because alpha equal to omega naught, this means this is the critically damped case. Since alpha omega, the response is critically damped. So accordingly, you see, everybody see here, I have chosen that equation. So again, I am coming back. Everybody see, this is meeting the second condition because alpha equal to omega naught. So just choose this equation. If you find alpha greater than omega naught, choose this equation. If you find alpha less than, then choose this equation. Everybody, could you follow me?
Yes.
Yes.
Okay, great. Yes. So therefore, because both are equal, so therefore, accordingly, I chose the equation. And then here I just calculated the value of S1 and S2 by using those expression. As I told you that you don't need to memorize, you will be just looking the equation. During the exam, you are allowed to look those equation and calculate. Your goal is understanding. That's fine. And then over the time, you will be able to memorize. But initially, you don't need to memorize. I would not encourage. Just you understand that how you will solve. Okay. Now, everybody concentrate equation number A. So this is my equation. But then there are two constants, A1 and A2. Alpha value is fine. You see, e to the power minus alpha t. Alpha you are getting here. Already we calculated. So you see, already I put minus 10t. But the question is how to get A1 and A2. Now everybody say, because there are two constants, you need to apply two initial conditions. So what are the two initial conditions? You see in the problem, two initial conditions. One is V naught equal to 0. Other initial condition, I naught 10 milliampere. We have to utilize these two initial conditions to find out those two constants. So if you have only one condition, then you can't solve. Two constants, you must need two initial conditions. That's the key to solving the problem. Now everybody see what I am doing. So this is my expression, weight is this, equation number A. At t equal to 0 time, V naught, you see, this is A2 multiplied by 0, 0, e to the power 0, this is 1, so I am getting only A1 from this one. This means A1 equal to 0. So one thing is solved. Now I have to find out the A2. What I am doing here, I am making time derivative, dv by dt of this expression. Everybody see. So dv by dt, and then everybody will see a1 multiplied by this one, then plus a2t multiplied. So there are two terms. So you have to do twice. So first you see a1 and then this one minus 10 e to the power minus 10 time derivative. And the next time a2, this one for t1. But for the next time a2t for this one minus 10 e to the power minus 10. Just I made time derivative. And then from here, e to the power minus 10t is the common factor. And then minus 10a1. From here, I am getting plus a2. From here, I am getting minus 10a2 into 10. Now, everybody say, this one I have written. We need to look this on how I get that on. Let me go. Yes, everybody see this one. For initial condition from equation J, we have the following. What was that equation J? Once again, let's have a look. everybody see the very first equation. I wrote down the Kirchhoff's current law at the very first time. That is the equation number J. So this means in this equation, this is like for time t, for any time t. But in this equation, if you put t equal to 0 time, then this means v naught over r. And then c dv naught by dt. But for this term will be, this one, I naught. So therefore, in this equation, I am considering t equal to 0 time. If I do that, then come back that I was showing you. Everybody see, for initial condition from equation J, we have the following. So first term is v naught over r plus I naught c dv naught by dt. Then from here, you see, I am just rearranging. My plan is to find out dv naught by dt. So finally, I got dv naught by dt minus in the numerator, in parenthesis, v naught plus r I naught over rc. So this v naught and I naught, those two are the initial conditions or the initial value. So therefore, I mean, when solving problem, you will be just taking note of this one. Either you can remember or you will be taking, you don't need to derive because I derived. You will be just taking note of this one. So everybody see this one? This one actually I put here. Sorry. Yes, this line, I was here. Everybody come back. That dv naught by dt minus. So from there I got this one. Everybody, could you follow me? Yes.
Yes.
Yes. So you will just remember this one. Remember means you will make it handy in your note. And then see what I am doing. V naught value 0. That was the initial condition. R value is 2. And then I naught value was 10 milliampere. And then in the denominator, put R and C value. So then I got minus 10 over 25. I mean, I just put in that format. You could use decimal format, like minus 0.25. So, but I did not do that. Minus 10 over 25 unit in volt per second because I am doing dV by dt. So now everybody remember that this is dV0 by dt value. But here I calculated the previously dV by dt. So my dV by dt expression is this one. Now I want to continue the problem and I want to utilize this one and this one. So then see the next one. We already got a on 0. At t equal to 0, dv0 by dt minus 10, 5, 25. That I just showed you. I mean this expression. And then this is the dv by dt expression. Here everybody put t equal to 0. So what you get? dv0 by dt. So therefore you see this will be 0. You will be getting, this will be 1. You will be getting minus 10a1 plus a2. So that's why everybody see I have written this equal to minus 10 equal to minus 10a1 plus a2. So from there what you are getting? We already calculated a on 0. Everybody see? At the beginning we did a on 0. So if I put that a on 0, so I put a on 0. So finally I got a2 is minus 10 over 25. And then substitute a on and a2 into actual expression of Vt. What was your solution? Everybody say this was your solution. Because this is for the critically damped response. This was our basic equation. Just substitute a on and a2. Once you do that, this is the volt, but I put the result in millivolt. That's why it looks like that. That's all. So therefore, the thing is that just you have to, try to understand the steps. First, for every problem, first find out alpha and omega naught. First, make a comparison. Either they're equal or this is greater or this is smaller than this one. Depending on that, choose the appropriate response. Overdamped, underdamped, critically damped. Choose the appropriate equation. And then in every equation, there will be two constants. Now, you have to find out those two constants. How you will find out? with the help of the initial condition. You have to utilize initial condition. You have to make the time derivative of the expression. Also, you have to utilize this one. And then just normal algebra. Finally, you will be getting the solution. Is everybody fine? Is there any questions?
I have a question.
Sure.
Yes. Can you go over one more time why A1 equals 0?
Okay. Very good. So therefore, you see, this was our expression, right? Equation number A.
Yes.
So, and then you see the problem. In the problem, there are two initial conditions. You see, at the V0 0 equal to 0
Yes.
and I0 equal to 10. So we have to utilize these two. So that's why here you see in this equation, put t equal to 0. At t equal to 0 time, V0, I wrote V0, put t equal to 0 in this expression. So this is A1 that I wrote like A1 and t is 0. So this term is 0 and this term will give you 1. So therefore, ultimately you are getting just A1 from here. So A1 is 0 because that V0 value is 0.
Okay. Thank you.
Is this fine?
Yes.
Yeah. And then next time, once you get the A1, next your target is to find out the A2. So finding the A2 is like this, a bit complicated. First, you have to make the dv by dt of this expression, or write down the expression, then use this technique. And I showed you like how it comes. I mean, this is coming from here, this one exactly. And once you get that one, and then again, you apply the technique. That's all. You just use the initial conditions. That's all. Therefore, everybody say another example, then it will be more clear to you. Okay, see this example. Everybody concentrate on this circuit. Again, I have written down the answer for you. Okay, but here everybody say there is one problem in the equation, in the statement. What is the problem? Problem, the initial conditions are not given. If you just compare this statement, everybody say the first one again. V0 0 was given, I0 0 was 10. It was given. But here you see in this problem, those informations are not available. So therefore, but you have to find out those values. That is the thing. That's how you see this circuit initially, it is not the source free circuit. Initially, everybody see leftmost component, there is a 40 volt DC source. So with the help of DC source, you have to find out those two initial conditions. And then other parameters are given. This R is 30. Oh, so here you see I have written t equal to 0 this switch. This means initially this switch was open. Initially this switch was open. At t equal to 0 time, switch is getting closed. This is 50 ohm resistance. This is 20 microfarad capacitance. And this is 0.4 Henry inductor. So therefore those values are given, but initial conditions are not given. So that's why for this problem, when initial conditions are not given, at first you have to find out two initial conditions. So therefore everybody see how I am doing that. Again, I have redrawn that diagram, 40 volt source, those things, and you see at t equal to 0 time, switch is closed. But we have to find out the initial condition before closing the switch. This means when the switch was open. Now everybody see. Oh, and then what are the two conditions? You remember, condition means you have to find out what was the voltage across the capacitor and what was the current through the inductor. Always for each and every problem, you will remember initial condition means you have to find out voltage across the capacitor and current through the inductor. Those are the meaning of the initial condition. So therefore everybody see, assuming that the switch was open, So look the topmost circuit. When the switch was open, this was the current flow direction. Current was going here, current is going here, current is going. And will there be only current flow through capacitor? Please answer. Will there be any current flow through capacitor?
No.
No.
No, great, because this is the DC. It will be open circuit. So there will be no current flow, but there will be voltage across the capacitor, right? Yes. So that voltage you have to find out. The current is not flowing, but what's the voltage? Everybody see? That I am finding for t less than 0. T less than 0 means before closing the switch when it was open. So first find out what is the current then. This means this is the current, and you know this will be short circuit. For DC, inductor is short circuit, right? Okay, can
Yes.
can you remember your DC circuit concept? If there is DC source, then inductor will be short circuit, and then capacitor will be open circuit. So therefore, ultimately, this is 40 volt source. Only two components are active, 30 ohm and 50 ohm. This is open and this is short. So this means, look my expression, I am finding V naught here, voltage across capacitor. First I am finding the current, 40 in the denominator, this 30 plus 50. So I get the current, and then current multiplied by this 50. I mean the voltage divider rule. Can you remember voltage divider rule from DC circuit?
Yes.
Exactly, this is the voltage divider rule. So therefore I got 25 volt. So therefore this is V naught. This is the first initial condition. Next, what I have to find out? I have to find out what is the current that was flowing through inductor. So therefore that is again that current, like 40 divided by 30 plus 50. So 0.5 ampere, but I have put minus sign. Everybody see? In the problem, the current direction, in the original problem, current direction was given in this way. It was not in this way. The statement is suggesting, assume this is your current direction. So that's why I have put a minus sign here, minus sign here. This means your initial current is minus 0.5 ampere. So now everybody see, we calculated these two initial conditions. Therefore, this is the thing, I mean, try to understand the difference between the first problem. In the first problem, V naught and I naught was given. So you did not do anything. You directly calculating alpha and omega naught. But in the problem, if the initial conditions are not given, that is your first task. You have to first find out the initial condition. Okay, so therefore now we got initial condition. And how does the circuit look like? Now come back to the transient condition. At t equal to 0 time, this switch is getting closed. So everybody see, this means this is the short path. This means left side component 30 ohm together with the 40 volt source is getting sorted out. So therefore look my new figure. Because this portion gets sorted out, everybody concentrate, this portion sorted out. So I have only this inductor component, like I rearrange the term, I have put, I'm restructured, I have put on the left side this inductor, this 50 is this 50, this 20 microfarad. Now this looks like that parallel source-free RLC circuit. Everybody, could you follow me so far?
Yes.
Yes.
Yes. So this is the thing. I mean, unless you can make this form, you are not able to apply to choose which equation to use, because there are three conditions: overdamped, underdamped, critical damped. Now you are in shape. Now find out alpha and omega naught. The similar way that we did in the first problem. Find out alpha and omega naught. Okay, I got alpha 500, but I got omega naught 354. You see, in this case, clearly alpha is greater than omega naught. So the response will be overdamped. And then find out S1 value, S2 value. So which equation to apply? Because alpha greater than omega naught, the first case. Everybody see, overdamped case. So I have to pick up this equation. So everybody see, I picked up that equation. I picked up that equation. And in the second line, I am substituting value of S1 and S2 here that I calculated here. And you look the last two line, S1 and S2 value. Okay. Once I put S1, S2 value, then you see in the expression I have A1 and A2, and then exactly the same procedure that we did in the previous problem. Now apply the initial condition. So how you will apply the initial condition? V0, V0. What is the at t equal to 0 time voltage value that we calculated? Look the initial condition, everybody. V0 equal to 25 volt. So therefore, that thing I am putting V0, that is 25. Then in this expression, put t value 0. So this is getting 1, 1. You are getting A1, A2. So this means A1 plus A2 equal to 25. So therefore,
Dr. Ali, I have
Yes.
to go. I have another class.
Okay, so I mean, in a minute, I will, in or 2 minutes, I will finish. After this,
Alright.
there is no slide. Yeah, but
Alright.
but you can leave. Thank you.
Alright. Thank you.
Thank you. Okay, so everybody see here that T0, T0. So this means this is on, this is on. So A1 plus A2 equal to 25. From there, I calculated A2 equal to 25 minus A1. Now again, similarly, make time derivative of this one, dv by dt. So I am getting this one, and then take the help of that one. Can you remember this one that I was discussing in the first problem? dv0
Yes.
by dt minus, yes, again the same thing, and plug in the corresponding values, v0 25 from initial condition, that is, and I0 is minus 0.5. I am putting minus 0.5, but finally it gave me 0 volt per second. So now compare this one, and then just by applying algebra, finally we are getting A1 value 30.16, A2 value minus 5.155, and then plug in A1, A2 into the actual equation. That's all, you are done. So therefore you see, I mean, a little bit, a bit complicated part this one, that you have to make dv by dt, you have to apply the initial condition, and you have to be careful in this part. And as long as you are doing with patience, with much attention, you are fully fine. Is there any question? Everybody, could you follow me?
Yes.
Yes.
Great. So therefore, once again, again, I am going to upload this on, because I am making recording. So you can listen to my voice again here, and at home by using your pen and paper, you redo it, then it will be fine. It's just a little bit lengthy, a bit complicated, but it is not like impossible. It is not difficult thing. You will be fine. And then again, listen to my lecture in the next class. Next class, I will be discussing, for example, not the parallel circuit, series circuit. Then what? I mean, the very similar analysis, exactly the similar process, but instead of parallel, it will be series circuit. And again, I will be doing 1 or 2 problems, and then I am going to assign you the first set of homework, so that like everybody will be fine. You will be able to solve each and every homework problem. Okay, so with that, then like I'm here, stop sharing my screen. So thank you everybody for joining, and then see you on Friday.
See ya.
Thank you.